Hi folks, Mr. Long here, just doing a screencast about logistic growth. So what we're going to do is analyze the logistic growth curve, do some calculations related to it. Just roughly, I want to show you a sketch of the logistic growth curve. So logistic growth is growth that occurs in nature as populations grow, but then eventually reach a point where they reach what's called their carrying capacity. So the curve is its characteristic S shape. There is a point of inflection right there, which is halfway up towards the horizontal asymptote. There is a part of the curve mathematically, but not real life, that extends into negative x values. Okay, so it's that characteristic S shape, and that's going to be the point of inflection there. And the value that we assign to the horizontal asymptote is C, which means that the point of inflection is at a y value of C over 2, because it's halfway up the curve. So here's our scenario that we're going to look at. So two students arrive at a school, say they were on a plane, and they've got some sort of infection. Not really serious, but gives everybody a chest infection or something, right? A chest cold, and but it's really it almost everyone does get sick with it because it's not a disease that anyone has immunity to in the school. So again, two students, 500 students in the school, and so we're going to use this equation right here to represent it. Okay, and the 500 means there's 500 students in the school. The 1 plus 299 makes 300. And 500 divided by, this one is going to be, actually, this one there's it's 1.67 students initially that have it. That's an oopsie. Oh well, that's okay. The mathematics are going to work out the same. So anyway, and then this right here is the rate constant, so that determines how quickly the illness is spreading. That e to the negative 0.4. Okay, so and in this case, it would be something like growth of bacteria. So you would have 1.67 milligrams at the start, and there's only enough area for the bacteria to grow to a maximum of, say, 500. So it wouldn't be, because there's a decimal for the y-intercept, it wouldn't obviously be people. Okay, so let's start going through this. The first thing we want to do is do a limit as t approaches infinity. Okay, so A is a limit as t approaches infinity of, our equation is 500 over 1 plus 299 e to the negative 0.4 t. So let's think about this. What happens to this as t approaches infinity? Well, it's e to the negative infinity. So e to the negative 1,000. So if you take that 299 and you repeatedly divide it by e an infinite number of times, e is about 2.7, I think you're going to get 0. So 299 divided by e divided by e divided by e repeatedly in an infinite number of times, you are going to get 299 times 0. So that's going to be, you're going to get 0 for that. So then it just becomes 500 over 1. So 500 over 1 plus 0 is, in fact, 500. So that tells us that after a really long time, the population is going to be that have succumbed to the illness, or the maximum amount of bacteria would be 500. Okay, so that's our horizontal asymptote. Okay, so the next thing that we're going to look at is the point of inflection. So this is really nice graphically. Now, normally you would have to set the second derivative, find the second derivative and set it equal to 0. But there's an interesting property of these logistic growth curves, and that's that the point of inflection is exactly halfway between the x-axis and that horizontal asymptote. So we say it's at a value of y equals c over 2. So in order for us to figure this out, all we actually have to do is set that logistic growth curve equal to C over 2. So let's go down here and take a look at what we did. So right there, that's the logistic growth curve, and we're going to set it equal to some value of y. Since the maximum was 500, we're going to set it equal to 250. Okay, so I've got, this is the equation right here that we're working with initially. So we have that equation and we work with it. So what algebra can I do? Well, the easiest way to do this is to do the reciprocal on the left side and the right side. So if I do the reciprocal on the left side, I'm going to end up with that divided by 500. And on the right side, I'm going to end up with 1 over 250. So what I end up doing then is I end up doing the reciprocal and multiplying by 500. Okay, so I'd end up with this right here. Okay, so it's reciprocal and multiply by 500. So you get 2. Now what's interesting is because it's halfway up, you're always going to get this equation right here. I should put this one in red. You're always going to get that equation right there to solve when solving for the point of inflection, right? Because the 500 is always double of this number at the point of inflection. And then, of course, it's obvious that even the next one will have to be always true, right? Because I'm always going to get 2 minus that 1. So we subtract 1 on both sides. So, in fact, I'm always going to get that equation. And then what I will always do is divide both sides by 299, which gives me that. And then I take the ln of it, of both sides, and I get that. And then I divide both sides by negative 0.4t. But what I want you to see in general is this, that this 299 is the a value, right? So it's always going to be a e to the kt equals 1. Okay, that will always be the formula that we end up solving for the point of inflection. So then e to the kt equals 1 over a. I then take the ln of both sides, because I've divided by a, and I'll get k times t equals ln of 1 minus the ln of a. And then I divide both sides by k. By the way, ln of 1 will be 0. So t is always going to be equal negative ln of a all over k. And that is a nice little shortcut to get the point of inflection every time. Negative ln of a over k. So when we go through that, we get t equals 14.25. Now, I know I went through that fairly fast. You may want to rewind and go through it again. But again, the basic idea here is that we took this equation, the original equation, right here, and we set it equal to 250 because we know the point of inflection occurs at a distance halfway between the x-axis and the horizontal asymptote. Okay, so the last thing we want to do is do some rates of change, okay, do some derivatives. So what do we know about the rate of change at the POI? Well, so C is rates of change. So we want to get y prime when t equals, and what was the point of inflection? 14.25. At t equals 14.25. So we know y equals 500 divided by 1 plus 299 e to the negative 0.4 t. So one of the things I would want to do here is reorganize this as 500 times by 1 plus 299 e to the negative 0.4 t to the negative 1. And then I can use my chain rule. It's a little bit nicer than using the quotient rule. There's a few less calculations. So it's just 500 multiples of this derivative. Okay, so y prime So we're going to let u be the inside, and u is going to be 1 plus 299 e to the negative 0.4t. Du by dt will equal negative 0.4 multiplied by 299 e to the negative 0.4 t, because of the chain rule, right? So then we go over to the other side, and y equals 500 u to the negative 1 dy by du will equal negative 500 over u squared, because it's u to the negative 2. So once we go through that, we can then write overall y prime is going to be du dt by dy by du. So in the numerator, we're going to have negative 0.4 times by 299 e to the negative 0.4t, and that's divided by u squared. Oh, what's u worth? By the way, folks, I forgot something. I'm trying to go through this fairly quickly. That negative 500 has to get multiplied in as well. So in fact, what I should have done is negative 0.4 times negative 500. Well, negative 0.1 times 500 is 50. Negative, yeah, 50, and then I've got 4 groups of that. So that's actually negative. Negative times a negative is a positive. So that's actually 200. So let me go and just erase this. We can see that should be 200 times 299 e to the negative 0.4t all over u squared, and u is 1 plus 299 e to the negative 0.4t. And that's important. And the reason I knew that I'd made a mistake is I know that because of the shape of the logistic growth curve, the slope is always positive, which means that this value has to always be positive, right? Because that is the derivative. Okay, so what you would do at the next point is you would sub in t equals the point of inflection, which we worked out to be 14.25, and sub that into the derivative and get that answer. And notice, it does make sense that, so the point of inflection is right there. That's the steepest part of the curve, right? So you're going to get the steepest slope. So that's when things are growing the fastest, or the most number of people are becoming ill, depending on the nature of the curve. And then in the other question I wanted you to do, I wanted you to find the rate of change for, so subbing into the derivative, for 5 days. So in this case, 5 days might be right here. So we would see probably a much lower rate of change because the tangent slope is much less. Okay, folks, so I know that you can sub numbers into an equation, but I wanted to go through that process with you, okay, for the logistic growth curve. Big thing is that you can figure out the horizontal asymptote, you can figure out the t value, the time value for the point of inflection, and get rates of change, okay? So again, look that over if you need help. I know I did go through that fairly fast, and certainly we did go through it in class, but I know a number of you have been away for a variety of reasons. Have yourselves a good day or evening.